So, in today's lab video, we will continue with our study of network models and perturbations and focus more on perturbations as well as profiling, which is a very interesting way to study your code and examine its performance. Okay. So, now let us get back to some of the problems we were talking about in the morning today, and particularly trying to perturb a graph and find out what is happening, right. How do you perturb a graph? Remove a node and its edges and then plot what? Plot L, plot diameter as it changes. So, for this, right, so it can get a little tricky. So, what you need to understand is, first is you need to have a way to perturb a graph, right, and what you could do is basically inside a for loop just remove every node one by one, or you may want to remove nodes in a particular order, right, maybe order of betweenness centrality not recalculated or order of degree not recalculated. That is the easiest place to start. You can do an incrementally tougher problem little later on, but initially you can start with that. Take a given, create a Barabasi-Albert graph or something, or create a random graph and see how it changes as you start knocking out edges.
So, deleting a node means we will just make that nodes row and column full 0.
That is it. So, that is immediately the next point you need to think about, right. What does it mean when I say delete a node, and how do you calculate diameter?
The matrix whichever has the maximum value 0 and infinity.
Yeah. So, which matrix?
Adjacency.
No.
Shortest path.
How do you get the shortest path matrix?
E pi.
It's a good idea, but that won't give you the distances, it will only give you the connectivity. There's something called all shortest paths. Look this up. My font size is too big, but it computes the weighted all pairs shortest paths. So, the single source shortest path problem uses the Dijkstra algorithm. This is an all pairs problem, so it uses a dynamic programming algorithm that is given by Floyd and Warshall. So, it efficiently finds the entire matrix of shortest paths distances.
Assuming it is having equal weights.
You can give weights also if you want. Mostly we are using unweighted graphs, but it can use anything. So, BGL has this misspelled, make sure you get the spelling right. It's N and Y, not Y and N. Let us see what are the other graphs that we can generate easily using BGL. Maybe we can use one of them for perturbation. Nope, it's got a clique, a cycle, Erdo-Shreni, grid. So, we will have to make our own graphs. Okay, let me see if I can. Anybody's gotten the rewiring right?
This should be You're calling it Yes, sir, Zero. So it will be two faults. We can random one fault.
Inside that you can do.
We have four columns for that particular one. Do
A
that
of
relation.
colon I or just A by.
For that.
checking the time like that. অন্য জায়গায় করতে হবে।
Okay. Okay.
অনেক কম কম্পিউটার মেমোরি লুপ লাগিয়েছি হ্যাঁ লুপ তো লাগিয়েছি একটাই লুপ লাগিয়েছি আমার এই দোষটা আমি তো দিয়ে বলেছি
If you don't have any, if
Makes the infinity of it.
Why only one laptop? Ranjit, no laptop.
I don't have any charge.
Go there, no? You would have a charger or not?
No, I didn't bring any charge. Tried.
You have a charger. Rohini, you have your charger.
No, mine is HP. You can come. Which doesn't have HP.
How is it going? Yes, Shantan.
Keep the notes on the basis of what?
Hmm? No, rank by degree or by between a centrality. First do degree. How is it going? It's fine. How did you understand it? So you basically want to create the adjacency matrix. Then you need to see what are all the, so for constructing the adjacency matrix, you need to find out what are all the nodes I need to connect to. So if your node is numbered 5, you have to, and you need to connect to 3 on each side, you have to connect 4, 3, 2 on the left hand side and 6, 7, 8 on the right hand side, which you can get by MATLAB indexing. So 6, 7, 8 is basically 5 plus 1 to 5 plus k, and 5 minus 1 to 5 minus k plus 1, something like that. And you will have a problem for nodes in the end where it will get negative numbers, for which you have to use mod function. Here are the different things. I think this is diameter, this might be characteristic path length, this is clustering coefficient. X-axis is beta, y-axis is any of these parameters. Hey, rewiring regular lattice. I think this is characteristic path length, this is diameter, this is clustering coefficient.
What is x-axis?
Beta, increasing probability of rewiring. This is 100% rewired, 0% rewired.
But there should be a significant increase in clustering coefficient.
No, that is compared to random, no? In rewiring,
Compared to random.
oh well, wait. No, you're right. So clustering coefficient decreases. So maybe this is not a good example to look at. We need to look at larger values, I presume. code is too slow. I have to optimize it.
1000.
So clustering coefficient, how does it change from a regular lattice? When you rewire, it should increase. Well, but no, the regular lattice is already very highly clustered. It's just clustered in a different way. No, what is the most interesting thing?
Characteristic path
This is
decrease
decrease drastically. That's something you clearly see. See, in one shot, my first simulation, it's halved. 10% rewiring and characteristic path length has become half. Which makes sense. I think this makes sense. No, this is far too slow.
5 neighbors and 1000.
So I'll just show you one interesting concept. Right. So this is just a simple piece of code that does rewiring, right? But when I run it, I feel it's quite slow. So it takes about 5 seconds roughly for one set of to study one set of rewirings. So it's a very interesting way to study a performance of a program. You can profile your programs, right? Now I just say this. I said profile on. And I'm now running the program. It's running as usual. So it's now almost finished. It's presumably plotted. The characteristic path length is sort of fluctuating here in this case. But what you can now do is you can view the profile which tells you where your program is spending its time. So it took a total of 76 seconds to run this program, out of which is that no, I think maybe 76 is between the time we started it and finished it, looked at the plot and all that. So study rewiring ran for 54.28 seconds, right? And it almost spent no time in itself. Self time is 0.013 seconds. It spent a lot of time doing this code called simple Dijkstra, which is used for diameter. Right? That seems a little slow. For example, all shortest path seems even faster. So looks like this is the killer here. So what we can do is let's okay, now let's try to repeat it. First, let's test it out. This already takes a few seconds. This takes all the time, right? Okay, diameter of 800 is 4. Is 4. This is fast, right? So now let's rerun the code. Oh, I had a typo. Ah, 4 seconds. So now where is all the time going in? You're doing set diffs. Yeah, can't really help some of those, right? So I'll show you one moment. So you click study rewiring. It tells you how much time was spent in each of these lines. So less than, so it made 11 calls to this, one call to many of these. It spent 3.65 seconds here. Out of the 3.65 seconds here, it spent 3.25 seconds in rand sample and set diff. And it spent 70% of the time in set diff and 15% of the time in rand sample. Can you speed it up? Can you avoid using set diff? Can you do something else? I think you can just set up some sort of a mask. Let's try that out. So this is how you actually debug a piece of code and make it faster, right? So you incrementally find out what is the bottleneck and try to get rid of that bottleneck. Sometimes you won't be successful. Let's say if you are successful here. So it turns out that the Dijkstra that this was using was horrendous for whatever reason. So I don't even know where that Dijkstra is coming up from. Let's yeah, this is from Cobra Toolbox. It's somehow a slowish Dijkstra. Fair enough. So now let's see, we want to speed up set diff. What is it that I'm achieving here? I'm trying to find neighbors that I do not have at the moment. Right? I want to rewire every node to a different neighbor. So I first find the existing neighbors and set diff, a minus b, set difference. A minus b, set A minus set b. So return elements in set A that are not in set B. So this is the list of all nodes from which I want to get rid of those that are present in my current neighborhood, right? So one way of doing this would be
That's what I'm thinking. What are the codes written? You want to include the year? Actually, this is all considered in the. That's what I think.
zeros, correct numbers is 1. So let's see. So how much time is this taking? So set diff takes 2.54 seconds. So what I can do is I can let's go to rewire lattice. That's where all the time was. So it's already changed the thing anyway. So copy to new window for comparing multiple runs. Anyway, this number you can imagine, no? It spent 89.1% in set diff, right? So let's try to run it again. Can you see the difference? It's now gone down to from 3.25 seconds, it's gone down to 1.732 seconds. Right? And now it's spending time in rand sample, which you really can't afford to, you can't avoid it. Right? Because you need to generate random numbers, you need to rand sample. So I think now we've hit the ceiling. I don't think you can make this code faster. But we essentially had. So what am I doing here? I'm first getting the bunch of current neighbors, and then I'm setting a mask, which is all zeros, and then I'm essentially trying to find out what are all the nodes that are not currently in my neighborhood. So I'm saying I'm first assuming that all nodes are not in my neighborhood and getting rid of those currently in the neighborhood, in a sense. So let's run this code now. That's really fast. Looks fair enough. Looks very similar to what we started off with. But now we can study it with more granularity. So you can use a larger lattice. Let's be ambitious. More steps. It's still respectable, right? Compared to what it was. This is going to take half a minute, maybe. This is not too bad, given where we started off.
Sir, if there is already edge, we'll omit it or we'll just.
What do you mean already edge? There is an edge.
We are going to rewire it.
You mean you already rewired it?
No, there are two edges. I'm going to.
No, there is no two edges. There's only one edge we are worrying about.
No, a node has.
We pick a node,
That has.
we find its edges.
That has say 4 edges.
Correct.
Out of 4 edges, 2 edges are less than the random beta we have. Like.
Okay. You want to rewire two of those? Yes.
What if I rewire like this? Like, take this and put it in that, take this and put it in that. That is also rewiring.
No, because it's already a neighbor, right? You wouldn't rewire it.
No, for this node, this is.
You're saying, okay, let's spell it out. You have A and you have C and D, let's say.
As neighbors of A.
As neighbors of A.
These two probability.
Yeah, so when you rewire C, you will never rewire it to D because D is already a neighbor.
Okay.
That's what I'm trying to do. So find a node that's not in my current neighbor list and rewire to that. Okay. So reword this x plus k, x minus k, find something else on the across the table and lattice and rewire it to it. So your question gave us enough time to finish the simulation. So let's look at. Look at this. All the action happens in the first shot, right? The first rewirings make a C change. The initial diameter characteristic path length is 35. It comes down crashing to 5 for a rewiring of 1 by 25, 4%.
For larger networks, the effect is more.
Well,
But they are only 0.1.
Yep. It depends. So it's not just large because it's a function of n, k. It's kind of complex. But yes. So you can see if you keep varying k, how does this graph change? If you keep varying n, how does this graph change, and so on. So in today's video, I hope you had a good picture of how we perturb networks and how we profile MATLAB codes to try and improve how fast they run and so on. But the basic concept is try to avoid loops because MATLAB never does loops efficiently. In the next video, we will switch gears and move on to reconstruction of biological networks. We studied a lot of tools and tricks to study biological networks, but how do you build these networks in the first place? Yes, you can get something of the string database, but how do you build these networks in the first place? So we will look at how do we reconstruct gene regulatory networks and some algorithms for reconstruction and the concept of synthetic lethality.